Good afternoon, everyone, or morning or evening, depending where you are. Welcome to the second episode of today's webinar, R&D Activities on Supercritical CO2 in Europe. My name is Jitka Spolcova, and I work for ETN Global, which is the organization that hosts this webinar today. If you were with us last time, you will surely remember that at the end of last time's seminar, we asked participants which topic they found the most appealing. And majority of participants found the most appealing component challenges. So this is what we are talking about this time. And in particular, we talk about compressors because this component was the most logical to start with. So this webinar is in cooperation with 8 European R&D projects, whose name and logos you can see on the screen. I will not go into details because the first webinar was dedicated to introduction of these projects. So you can refer to the recording of the first webinar and the presentations if you want to know more about these projects. We tried quite hard to make this webinar interesting, engaging, relevant, and maybe also a bit entertaining. But I will have to go through a few points that are not so interesting and entertaining to have the seamless webinar experience. So as you can have noticed, probably this webinar is recorded, and it's because we would like to offer you the recording after the finish of the webinar. I would also need to ask you to switch off your mics and your cameras unless you speak. I cannot mute everyone because if I do it, I will also mute the speaker. So I will ask you to mute your mics now. Thank you very much. And this brings me also to another point, questions and answers. There is a dedicated session at the end of the webinar, but if you want, you can already address your questions towards one of the speakers during the session, and our speakers will do their utmost best to already answer these questions during the webinar. No question will remain unanswered. If there is too many questions, either orally or in writing, we will do it after the end of the webinar and share the answers. Another thing is your smartphones. Please have them charged and ready. There will be 2 Slido questions, so they will be very handy. And the last point is that you don't need to take many notes unless you really want to, because we will share not only the recording, but also the slides after the end of this webinar. The next slide is about who are the charismatic speakers that will be your companions of today. So the first one is Giacomo Persico. Giacomo is associate professor at Politecnico di Milano. He works on turbomachinery and focuses especially on sCO2, organic Rankine cycle, and wind turbines. And within the sCO2 EU research, he's participating currently in the Cool Heat project. He's author of many publications, about 180, and out of this number, 60 appears in journals. The following speaker is Marco Ruggiero. Apart from being a talented musician, Marco is also a senior engineer at Baker Hughes. He graduated as mechanical engineer from the University of Florence, and he has his PhD from the same institution. Baker Hughes has been lucky already for 22 years, having Marco working on different R&D programs. His current assignment is external funding and technology development director. And the third speaker is Rasmus Rubycz. Rasmus holds his degree in process engineering from the University of Applied Sciences in Cologne. He uses his technical talents also for restoration of classic cars. Apart from that, he has been working for Atlas Copco since 2012, and nowadays he's serving his customers as marketing manager for a segment that he finds very exciting: new energy and energy recovery applications and systems. So, and obviously the next part is the Q&A that I've already announced. So we are almost ready to dive into compressors, but before we do it, I will ask you to take your phones, because this is the time for the first Slido. So please scan this QR code that you can hopefully see on the screen. And when you are done, we have prepared quite a simple question. And the question is that, according to you, what aspect is the most worth studying in the sCO2 power cycles components? If you can limit your answer to 2 or 3 words, it would be great, because then the cloud becomes a bit visible if the answer is much longer. You can choose more answers. And obviously you can choose the answers of other people as well, so that we can see what aspect is becoming the most popular. I see that there are still people typing answers, so we can still allow a few more seconds or tens of seconds. For the time being, the cloud looks like a PR for the session, because we see the compressor is the winner, but it's not us, it's you. We still have a few people typing, but maybe I can already ask you, Giacomo, if you could start debriefing on what we see, and if you could see and tell us if this is something that you have maybe expected.
Yeah, so first, thank you, Jitka, for the very, very kind introduction. Good afternoon, ladies and gentlemen. Thank you for being here. And I hope you will receive some nice information and useful information, especially. My role in this webinar will be to introduce the challenges from the scientific perspective, so to leave them the floor to Marco Erasmus for their industrial experience about that. It's nice to see that a compressor is a big word here, showing that this is that the people are very interested in the topic. And as soon as Jitka, you say that it is okay, I can start sharing my slides.
I think we are done, you can.
Yeah, okay. So let me know if you see the slide. Is it okay?
Yes, yes, we can.
Okay, then let's start. As I was saying before, then let me activate the pointer that will be needed afterwards. We can identify 2 main configurations for sCO2 power systems. We start from that. One is the more known supercritical CO2 configuration, and the other is the transcritical configuration, which can be based either on CO2, pure CO2, and CO2 blends, so CO2 with dopants. The main difference between the two, among many other things, is that for what pertains our meeting today, is that in the supercritical case, the compression is obtained in a near critical compressor, while in the other configuration, the increase in pressure is obtained by a subcritical pump. Focusing first on the supercritical case, and so the near critical compressor configuration, this is basically a Brighton cycle, single phase, closed. And the key idea for the success of this cycle is that the compression occurs close to the critical point, reducing the compression work. This also means that we will have to deal with high density fluid that will have as an implication compact machines in small size. But these can also become problem because the near critical state at the intake of the compressor introduces thermodynamic challenges. And also in case of low, let's say, power capacity of the plant, this will lead to a very small scale machine, and this can be problematic from the manufacturing point of view. If we consider now the transcritical cycle, it is basically a Rankine cycle. So the work to increase pressure is even lower because it is done in a pump, and the presence of a pump offers the opportunity for a standardization of the component. Moreover, the use of blends with the CO2 allow changing the critical state and to extend the application of this kind of cycles also for high ambient temperature. However, from the point of view of the cons, focusing on the pump, we can imagine issues for the cavitation of this CO2 pump, especially in case of blends, and also compressibility effects. But we will come back later to these aspects. Let's start for speaking about SO2 compressors. Let's start from the basics as much as possible. We are all used to operate with ideal gases that obey to the ideal gas law from the volumetric point of view, and whose thermodynamic behavior is summarized in the coefficient gamma, so the ratio of specific heat capacities. However, this parameter for ideal gases is also equal to a quantity which is some kind of an index of compressibility that is also called K. But we said that the idea in our case is to operate close to the critical point with the compressor, and close to the critical point, the thermodynamic behavior of the fluid deviates from the ideal one, and we measure this deviation, this non-ideality, through a parameter Z, which is much lower than one close to a critical point. You can see here the regions where the Z is smaller than 1, and it is much smaller close to a critical point. However, this is not the only thing. In that region here also, it comes that the compressibility index K is different from gamma and depends on the thermodynamic state and grows as the entropy reduces. And we can even prove that K replaces gamma in the relationship between the head coefficient of a compressor and the pressure ratio of the compressor. So this means that when operate with critical condition in the near critical state, depending on the thermodynamic state, we will see an impact of the thermodynamic state on the pressure ratio of the compressor. We will come back later on this point, but this is not the unique thing which is relevant for these cases, because working close to the critical point also means to work close to the saturation curve. And in this case, due to local expansion and acceleration we have at the intake of the compressor, we can have the thermodynamic state dive into the dome, promoting phase change, especially phase change that can be, as in this case, a cavitation, or if you start from the high entropy condition, condensation. And you can have situations like this one represented here, in which you have regions of single phase flow and other regions close to the blades where the acceleration induces phase transition. Phase transition has a lot of impact from the structural point of view, but also have an impact from the thermodynamic point of view and fluid dynamic point of view, because to a phase change, you have also in connection a huge drop in speed of sound. This drop in speed of sound creates a huge rise in Mach number and can actually produce an anticipated choking, which has an impact on the compressor rangeability. Here you can see experimental and computational results on 2 megawatt scale compressors tested in Europe and in the United States. This one, it was the Scoflex compressor, and this is the Apollo compressor. And for both of them, experiments showed that there is a huge change in the rangeability of the compressor, passing from a far to near critical state. So if we summarize all this information, the take-home message is that the thermodynamic state at the intake of the compressor has a huge impact on the behavior and the operation of the compressor from several point of views. We did, for example, a study in which we consider for a single compressor 4 different operations. So on the left, liquid-like, on the right, vapor-like, on the top, supercritical, on the bottom, subcritical, and the same compressor operated in these 4 conditions produces very different operation maps, a very different compression ratio due to the change of the parameter K we introduced before, moving along that area, and differences in the efficiency of the compressor due to changing in the let's say flow field and velocity triangles, and also huge change in the extension of these curves, so difference in rangeability due to phase change. So all these things must be mastered when a supercritical CO2 compressor must be designed and operated in practice. However, these thermodynamic aspects are not the unique aspect we should consider, because there are also technological considerations to be included in our analysis. Of course, these things will be discussed in much more detail by Marco and Rasmus afterwards, but I will give you some ideas. These are basically machines that operate with a fluid in high pressure and low temperature. So they will become compact machines that operate with low volumetric flow rate. So in several cases, the most efficient configuration and architecture is radial, and even requires specific strategies for low flow functioning pedals. In these machines, we can imagine to have limited pressure ratio per stage, around 2, and even considering the high density, this turns out to be a relatively acceptable level of mechanical stresses in absence of effects of creep, and this allows to use relatively conventional materials, even though some supply chain issues can occur, especially presently. But the most challenging aspect from this point of view is that moving from far from the critical point to close to the critical point, the size of the machine greatly reduces. And because of that, manufacturing issues can arise, for example, in the dry gas seals or in the surface roughness. So question arises in the fact that there exists a minimum compressor size that is feasible, and does this produce any limit in the minimum power capacity of a supercritical CO2 system? So all this consideration leads us to, let's say, towards some kind of classification, possible classification for the selection of SO2 compressors. That originally this was proposed in the chapter by Musgrove and Wright in 2017, in which they identified 4 ranges. For power capacity, not of the compressor, power capacity of the system below 1 megawatt, we have a very compact, very fast machines. So the question arises if this is really feasible. For power capacity in between 1 and 10 megawatt, machines are compact and fast, but still feasible. And this is a very interesting area of application, for example, for waste heat recovery. As we move towards higher power capacity, we start to see that also axial compressors can become interesting and relevant, and above, especially for 50 megawatt and above that level, and above 300 megawatt, it seems that only axial compressors are effective. So the first question is, are these thresholds reliable? And this is something that needs technological research and development, but this opens also the way for other questions. That when we think to axial compressor applications and axial compressor configuration, and we combine it with the high density of the fluid, the question arises on how and in what way these machines can withstand, and especially the blades, with such aerodynamic forces. Should we think to novel shape of the profiles, thicker profile that are still efficient? And as a further consideration from this, maybe when the power is so high, could it be more interesting to consider pump-based transcritical cycles because they are inherently not suffering from, let's say, this scale effect. And this question somehow gives us towards the discussion and the presentation of the challenges about the pumps operating with CO2 and CO2 blends, which are devices that can be quite, let's say, different and with a different complexity with respect to the SO2 compressors. They operate with a supercritical fluid in liquid light thermodynamics and still have issues of small size. So focusing first on the thermodynamic aspects, yes, they are liquid, but in a compressible liquid condition. So issues can arise in a thermodynamic, since the machine operates in a thermodynamic region not very consolidated, especially for CO2 blends. Also, we should consider that the change of phase can occur also here, but in a different way with respect to what we have seen for compressors, in the sense that if also for compressor cavitation can occur, CO2 compressors, but this kind of cavitation is different because the condition of the fluid is subcritical. So the specific volume of the vapor is much bigger than that of the liquid, and the bubbles are not, let's say, dispersed, and their implosion can become critical from the resistance of the material. And also, we need to develop criteria to avoid cavitation, but this requires more research, especially for blends that have a novel thermodynamics. From the technology point of view, just a few words that also pumps share the problems of small size. So also here, the same question arose for compressor applies also here. What is the minimum size? But also we should consider that from the techno-economical point of view, pumps offer the opportunities for standardization and scalability. So these are both aspects that should be explored in the future. And we start to see some information about that from the next presentations from Marco and Rasmus. For the moment, I thank you for your attention, and I leave the floor now to Marco.
Thank you, Itka, for the introduction, and Giacomo for setting the scene. A lot of what you said, I won't be repeating, but I will go in, let's say, in the practical details of carrying out research and development in an industrial context. So basically, this is what I'm going to talk about, and hopefully now I will leave enough time at the end for Rasmus to be on time and some question and answer at the back end. So first of all, no, I just want to remark that Baker Hughes is an energy technology company. We took upon ourselves to become one of the main players in the energy transition, and are working on a lot of different energy-related technologies to help our customers and the planet use the most clean energy possible. Giacomo mentioned a experimental activity done here in Europe and across the globe. We did build a test rig in our facility in Florence, where we tested the 5 megawatt compressor that was designed for the CO2 Flex project. The facility is quite large, as you can see. You probably now can understand the size of the facility by looking at the exhaust stack of the G10 gas turbine that is there in the middle of the picture. Being a G10, we have about 10 megawatt power available for driving. Currently, we have a gearbox installed, so we can run up to 4K RPM. It is possible to run a two-phase compressor, so that was not needed for this particular application, as two stages are and one phase is more than enough to get from the 70-something bar to the 260 that were the design point for the application. but the test rig is designed for taking pressure up to 760 bar. So, and that was rather a challenge. I mean, if you're familiar, these are all AP15K piping and valves and flanges, and you don't buy them off the shelf. You drill a hole through a solid steel. So the compressor that we tested had a couple very innovative for the compressor that we were used to see for CO2 features. The first being that it had a stacked rotor. So this is something that we have done. Just to mention one of our other products we have, it's the high pressure ratio compressor, which has a stacked rotor using heat connections. But for a configuration like this barrel type compressor, it was the first time that we did. So it was also kind of interesting to see how it played out, especially looking at leakages for a compressor which is overall, even though it's 5 megawatt, rather small, how the leakages in through the rotor also and the tie rod would play out. We also have a variable geometry IGV, which is something not entirely common in this type of compressors. And yeah, also this was done in order to fulfill the idea that we had on the project to achieve a very large operating range for the compressor. We would then be achieved by using IGVs and the variable speed motor. So using a combination of the two would have let get in between 20% and 100% of the operating range of the compressor. So what did we learn? We learned one thing, which I mean might be something already known, but the suction control temperature is critical. So even the variation in ambient temperature due to the time of the day are critical. So there is an inertia in the media that we used for cooling. We used water mist type coolers, and there was also not very hard or impossible, but took some attention in order to maintain conditions, as a small swing in temperature can have a very large swing in density, and that means that you're going off the map as you operate the compressor. Giacomo mentioned now the modeling that we've done together for the CFD simulation. So the results that we got from the extensive campaign did really agree a lot on the theory that we've put behind those simulations. So we are pretty pleased that not only now we observe the behavior, but we also have already a model for it. And this kind of predictability is what we always look for when we design new stages for a service like this one. One of the things that we were mostly concerned of is that looking at the stability map, this type of compressor was way off what was considered safe. So we took a lot of attention, and design effort was mainly focused on attaining rotor dynamic stability. As when we get to very high pressure, or let's say very high delta P across what usually are inactive components, so sealing and at the shaft ends, they can become an active component in rotor dynamic and damage your stability. So this was not the case. So the design that we achieved showed very good stability. So that's one of the things that we were worried about, and it didn't come to pass. So, and again, it's something that the behavior of the shaft and seals has always been, wouldn't say an issue, but potential trouble for operating this type of machine. So what are the challenges? So what we see as a challenge is for a Brayton type cycle is maintaining compressor inlet temperature. Not only through ambient changes, but also load changes. As the cooling media inertia or the exchanger itself might lead to transients that are taking you away from the point of optimal efficiency. There has been proposals to use density as a controlling parameter instead of pressure or inlet temperature, but so far the ways of measuring with accuracy density in such conditions are very limited. So that's one thing that is a challenge that would, I mean, as a compressor manufacturer and operator, we would gladly welcome. The effect of saturation condensation that Giacomo described, those during the design phase forced us to develop a new aero configuration, which also include splitter blades to address and ride the effect and be able now to properly design the performance of the unit. The operation of the dry gas seal, which is still one of the critical things that we see, especially in the transient conditions. One of the key elements, and has been proven somewhere else in the world, is that if you don't manage the buffer gas properly, you can lead to solid formation in dry gas seal, and that is let's say cause for critical failure in that particular component. So this is something which, even though not particularly challenging, needs to be very much looked upon with care. Looking at scalability, we see radial machines operating up to 50 megawatt. After that, we'll need to gradually migrate to full axial. So where the two technologies can live, probably an initial front stage axial would be enough to guarantee the right mass flow, the overall mass flow. But then as we move up in power and the size of, at least for the CSP application that we see and is currently perceived as the right one is 100 megawatt, there is a full axial machine. That means now that we introduce some of the challenges that we have in axial machines for lower pressures, which is now introduction of flutter or the importance of the first flexor mode on the blades, on the first stage blades, where we operate in an environment which has very high density. So the effect of forcing versus damping is not really known, especially looking at the large variations of density due to temperature changes. So this is something that really needs to be investigated in details as we move up in size in this type of machines. On the other hand, if we look at which is the smaller machine that we can produce using this technology. The defining factor, as we see it, is the weight of leakages on efficiency. So how much the leakage through the impeller and shroud annulus and the other leakages is compared to the main flow. Also, the manufacturing effect is not negligible, as there are some non-scalable geometrical features which will become relevant if we go below 100 millimeter diameter. So those will have also an impact on efficiency. So these are the challenges that need to be overcome on compressors.
Marco, I need to say that, but I'm afraid that you will need to conclude.
Yeah, okay. So the let's look at the pumps. So pumps as an item as still a not well characterized EOS in the liquid-like lesion. So that makes it challenging in designing. There is a high density variation through the pump, and there is also a challenge for the pump itself. And inlet conditions needs to be properly designed in order to avoid cavitation that might be, let's say, catastrophic for this type of machine. Scalability, we see an upper limit of about 1500 square cubic meter per hour as a volumetric flow due to size and forces, but also a limited scalability downward below 300 specific speed as we change type of pump, basically, so it becomes a volumetric pump. And the same applies for non-scalable geometric features below 100 millimeter diameter. So the conclusion is that we have a consolidated experience in SCO2 pumping. I didn't mention it as I jump on the slide, but this is a typical application for enhanced oil recovery. So we have been producing this type of pumps for a while, not for blends, but for pure CO2, yes. So it's something that it's on the market, and it's something we have experience with. We tested in Europe the first full-size, full-scale SCO2 compressor, which is a very good results in our opinion. And the next step is that the drag seal leakages recompression system needs to be looked at, especially for blends, as this is also something which is synergistic with expanders. So you don't want to waste some of the loop gas that is evolving into the gas loop in the atmosphere, but wants to recover and get it back into the loop. And that's it. Thank you.
So yeah, thank you, Marco. I will take on now as the last one here with our industry experience on the compressor part. And I start a bit earlier as well on the fact which development was rolled out in the industry to bring this whole thing that we call now an sCO2 compressor to a technical possibility. So we are leveraging the decades of experience we have with CO2 handling here for this next generation of CO2 turbo machinery. Just one word about Atlas Copco, international group of companies. Why I'm showing this? Because same as Baker Hughes, we are a commercially driven company. So that means in the end, all the projects need to have a certain economic aspect behind that. We are not a research institution primarily. Atlas Copco is a pretty has a pretty wide product offering, from mobile compression of a vacuum technique for semiconductor industry to these air compressors, probably everybody of you knows. And we are part here of the Atlas Copco Gas and Process division, means we're the tailor-made equipment suppliers in the, let's call it, retail store. Okay, so we learned already a thing or two about sCO2 And especially when the previous speakers were mentioning the differences between sCO2 turbomachinery design and normal machines, you can get this by the point comparing sCO2 with air of the same pressure and the same temperature. So just say 74 bar, which is slightly above the critical point of CO2, 31 degrees Celsius. Then the air has a density of 85 kilograms per cubic meters, whereas the sCO2 is at nearly 500. So this means like roughly 5 times or 6 times heavier. And the second nasty property of sCO2 is the fact that it can diffuse into elastomerics. And once it's in there and pressurized and you depressurize the system, you can have explosive decompression. This is something you want to avoid because otherwise you have to replace every time your static sealing elements. So air is like a feather and sCO2 is more like a brick. And the properties for these elastomerics, they also have to be very finely tuned. Okay, so we learned already by now, it's not just another gas. If you compare again here, the typical turbo compressors and expanders we do and other suppliers do with sCO2, then you see that the average of our machines goes from 0 to 50 bar, while the sCO2 machines would go from 30 to 300 bar and even beyond, as Marco just said, 600 bars. That's something you need to have for having the system efficiently operated. Temperatures can be low on normal machines, but with sCO2, especially in waste heat to power systems, they will be really high because, again, here, Carnot's law, the higher the temperature, the higher your efficiency. Power is comparable, but at the same time, the impellers, as we already learned as well, will be much smaller on the sCO2 because the density is higher. And something that I find pretty handy to imagine is if you take now the diameter of a normal impeller and you take the power rating of this impeller and you divide it by the square centimeters of it, then you have the, let's call it, the rating or the specific power rating of the impeller. And even on high power air compressors, it's going up to 0.8 kilowatt per square centimeter. While on high power sCO2 expanders, it goes up to 20. So this is, again, not just, it's more than an order of magnitude more, and it shows you what a strain and what a tremendous power sCO2 can bring. This, on the other hand, brings, of course, many challenges to the whole hardware of the machine. Looking at the shaft seal, it needs to be able to withstand those high temperatures and pressures. The volute of the housing, or the housing of the compressor, needs to be capable as well for the high temperature, pressure, and cyclic loads. If it's a small machine that needs to run daily start-stop operation, then you have to consider fatigue and everything. The impellers, they need to be able to withstand these high temperatures as well as this high power density. Of course, a lot of power on small impeller means you have high torques, high strain, and everything combined with high tip speed. That's a nice recipe for a challenging machine design. The guide vanes, of course, high density means high load on that. The pinion needs to be capable of the high torque, and the bearings, they need to hold everything together. So you have a nice variety of challenges. But it's not the first time that we are doing CO2 machines or that the industry is doing it. We just learned that there is a full-size, full-power compressor by Baker Hughes, and I will not go down here to every detail. The sCO2 compression and sCO2 usage in industry has already a bit more of a history, going down to the discovery of this critical point, the first full-scale commercial process utilizing the sCO2 for making urea, then the first use of these integrally geared compressors on the radial design, the first use of a dry gas seal, what is also a critical component for this machine, and then the first large integrally geared compressor with intercooling for CO2 compression. And then the first time we crossed that border of supercriticality in 2008 with a 6-stage compressor going to 83 bar, and then going into the development of high-speed dry gas seals under severe conditions together with an OEM. To the next stop, the 8-stage SCO2 compressor up to 200 bar, compressors for oxy-fuel power plants like the Net Power in the US. Also using SCO2 as power cycle fluid. Development of a small size waste heat recovery compander for the smaller power rating to leverage these nice properties of the SCO2 compact machines and so on. And of course, now going the other way, also using this fluid for heat pump purposes. Yeah, and to find out how it all fits together, of course, you can calculate, but you have to do as well R&D activities. Therefore, same like Baker Hughes, we set up a test stand and we tested in our facility the dry gas seal in collaboration with the seal OEM in a special mock-up here. And the target was to qualify this dry gas seals for the severe conditions in supercritical CO2, larger than 200 bar and 200 degrees. And after that, we learned some very useful lessons and implemented that into the first commercial project using this 8-stage compressor for going up to 200 bar. And another experiment we did was simulating the behavior of SCO2 around the critical point, and we verified that as well in the test bed. And we used this data output to calibrate our CFD and our database. So we have kind of an iterative correction of our mathematical models, and this leads to more precise predictions. And same as Marco said, of course, we like it if we can predict something before it happens, because then we are much more, let's say, secure that everything will work out the way we planned it. So I said we leveraged the experience we gained over the years. And now I want to show you some examples of large power CO2 compressors we did in the past. This is a carbon capture machine delivered to the Netherlands. It goes up to 22 bar. This is not yet supercritical, but it's also not a small machine with, as you can see here, nearly 3 megawatts of power. And this is one of the machines that first crossed the border to supercriticality with a 6-stage compressor layout and a power rating of almost 10 megawatts. It's going in the supercritical range, as you can see here, 82 bars and 87 degrees. And this machine is not producing any power in a power cycle. It is going into a chemical factory. So it's a process motivated pressure level here. This is the machine that we tested the seal for, and this is going into an urea process in Russia, and it's bringing the CO2 up to 200 bar. So this means it's really all in. I think the last 2 stages are supercritical. As I mentioned already, the net power system is a supercritical power cycle, and we supplied the compressors for this. But if you're interested in this, we can supply you additional material. Here, the compressors are not really working in the supercritical power range. Okay, and if we would reverse this whole process, as I said, just think about this. If you want to get heat out of a low-grade source, of course, then you need to invest electricity or driver power in this. And the reversal of these processes is then just called a heat pump. And sCO2 has some nice properties when used as refrigerant in a heat pump. That is the same beneficiary aspect, the high power density. And because of this high power density, you can end up with systems that are delivering up to 50 megawatts of thermal output per system. And at the same time, sCO2 has some useful aspects as well. no ozone depletion potential, and its CO2 is the benchmark for the greenhouse potential or the global warming potential of these refrigerants. Pressures, of course, are also in the normal high range, 200 to 300 bar, but we can reach as well very high temperatures from very low heat sources. So when Europe needs to decarbonize now to end dependence on the import of fuel, then we are one of these cornerstones or pillars, maybe a large-scale heat pump as well. Summarizing everything, for us as well as for the rest of the hardware and rotating equipment industry, the thermodynamic and the fluid properties are the challenge. It's, of course, all about predictability, knowing what you deal with. So learning our lessons together with other colleagues as well, finding out the right materials, refine our current material selections, what elastomeric materials may be used to what temperature and pressure, what metals can be used for what, improve our performance of the sealing systems, especially also as what Marco said, lower leakages, higher operating temperatures and pressures. Reducing leakages means you have higher efficiency of the system, and of course, then apply all these technologies you learn in one sector to the other sector to have these leverage effects that a heat pump will also profit from the new things you found out for waste heat power systems. That's it for my part. Thank you, everybody. And I'll leave it now to Jitka for closing this session.
Thank you very much, all the three speakers. I think that your presentations were very interesting, and I hope that all the participants also found them very insightful. And as I promised, there will be another Slido, so this is the time. So I will again share my screen. I will show you again the QR code in case you need it. So please take your phones. And this is the question that we have now. So we would like you to tell us what pops up after you have heard all the three presentations. So if you define all the three presentations that you have just heard by one or two words, what will they be? So again, you have an option to say this a few times, so you are not limited to one topic only. You can say that a few times. I think that the cloud is becoming very inspiring. Therefore, I will again ask Giacomo if you could please come to the stage. I leave it to you to make comments and to debrief on this cloud.
Sure. Thank you, Jitka, again. Thank you to Marco and Rasmus again. I think that we can summarize in also ourselves in a few words the challenges we discussed, that were the aim of our webinar, and challenges that we have seen are about the compressor operation in testing and compressor design, considering aerodynamic aspect and also dry gas seals. Then also modeling aspect that we did not discuss in so much detail because we wanted to focus on the technology itself, but then we will say some words answering to the questions, and aspects related to the applications. We can see several applications, several branches of application, and challenges with the aerodynamic design, for example, for XL machines, and challenges connected to the small scale, so very high scale and small scale. So now we heard a number, let's say 100 millimeters as a limit. That we still have to let's say discover in detail, but we start to have some ideas. I think we can also try to answer to the questions. I don't know how much time we have, a few minutes, but we received three written questions that I think they, let's say, deserve to be read and answered. So the first one is from Dinesh. I hope the pronunciation is correct. I think it could be for Marco. Can you comment about the challenges associated with instrument uncertainty when testing the compressor near critical point, and also its implication on the performance?
Yeah, thanks, Dinesh, for the question. I would not only talk about uncertainty, instrument uncertainty, but also on the effect of the high density to which quantity are you measuring. So now, let's think about the usual setup for operating the machine. You have one thermometric well installed, sticking out in the flow path. So with such a high density, you will always be somewhere in the middle of a static temperature and a total temperature. So and the high density means and the swing in density as the temperature change means that that is in itself a very high source of uncertainty rather than the instrumentation accuracy or uncertainty which you can calibrate. And that's why, and it was proposed first by Professor Francesco Casella from Politecnico di Milano. Since the density is much more flat in that region, we should find a way to actually measure density instead of pressure or temperature to control the units. Now, how you go about doing that in a 600 kilogram per cubic meter environment is another thing, but the implications are rather large. I mean, going off by half a degree means you go out of the map, and I think Rasmus can now testify the same. So it is critical, and there is no really one way to go about it.
Thank you, Marco. I think it is a quite extensive answer. I know that Dinesh will be happy about that. Second question, what is a typical range you see? And this is from Lucas. What is a typical range you see on actual suction volumetric flow for sCO2 compressors? So this is dependent on mass flow, power output, but can you give us a feeling? Rasmus, what do you think about this?
The typical range, I don't know if he's speaking about volumetric actual flow or normal flow, but the typical range starts in the range of a couple of thousand kilograms per hour, and then just goes up, speaking about a mass flow range, in the range of some 100,000 kilograms per hour. So we are speaking about the range from some 1,000 kilograms to some tons an hour. If that clarifies that. I mean, with sCO2, yeah, it's not about the mass flow we have in there. It's more about the power output or the heat you pump with the system. So we can look, of course, at detailed cases if he wants to be a bit more of a specific one. I think it's more relevant to say how much power you get out of a certain stream and how many kilograms per hour does that require.
Thank you very much, Rasmus. Then, if we have time, we can answer to the third question, still from Dinesh. I think this is for me. Can you please highlight a bit about the process and the limitation of the barotropic modeling approach to capture the two-phase effects? Can this be reliably used regardless of the inlet condition or there is some area where it requires further verification? And also, what is the role of selecting the total entropy value when developing the barotropic model? So the barotropic model is a model we developed together with Baker Hughes a few years ago, trying to simulate with in the most simple and robust way the flow in an sCO2 compressor with two-phase. Basically, it is from the two-phase flow modeling is an homogeneous equilibrium model. So it is reliable in the sense that it behaves like an equilibrium model. So in that neglects the disequilibrium that can occur between the two phases. And we know from literature that this kind of disequilibria, because there are more than one, becomes less relevant close to the critical point. And so in the supercritical condition, it seems strange, but it is the case. In the supercritical condition, such a modeling based on equilibrium works, not only for this application, but also in other applications and with other fluids, for example, for ejectors and so on. We have actually validated this model against experiments in nozzles, and in this condition obtaining very good results. And we also did a validation study in the frame of the SCO2 project, I mean, from CFD with the barotropic modeling and the experiments of the compressor. And it was important to say that we did this for multiple conditions. So if you remember the classification that I made at the beginning, so from, let's say, liquid-like to vapor-like, and in all the conditions, we got very good results. So, of course, this is something, a developing model, and I mean, we need to get more and more experience, but so far we can use it reliably. And regarding the intake state, we normally consider the entropy at the intake state, and in the barotropic model, you select pressure volume law according to a thermodynamic condition, thermodynamic transformation. And we normally evaluate this law along the isentropic one. And depending on the point at the intake, you should use a different transformation. You can refine it considering the actual, let's say, dissipation you have in entropy production, but this is a very minor effect for the typical level of losses you have in a compressor. Let me check if you have other questions. No, I mean, there are two comments from Alessandro and Dario that provides very good insights into the answers that me and Marco gave before. And that's it.
And Giacomo, in the meantime, I looked up for a typical case some reliable figures. So for a 2.5 megawatt output waste heat to power cycle, the typical flow rate is in the range just below 200,000 kilograms an hour, what is equal to roughly 90,000 normal cubic meters of CO2.
Thank you very much. Very, very precise. That's something we needed for the answer. I don't see any other question.
Maybe there is anyone who would like to ask the question directly.
Yes, maybe Gabriele raised the hand before.
Yes, hello, sorry, I was not able to find out the way to write the question before. I just would like to have your comment about the type of stages that have been used so far on the compressors. I notice, let's say, the picture from Atlas Copco compressor looks to have not so much back sweep stages, and also the curve from Becker Hughes seems relatively flat. Let's say, there is any specific reason considering, let's say, the relatively high molecular weight?
Marco, do you want to start first, or shall I?
As you want. Just quickly. First of all, ciao Gabriele. A long time I don't see you. Former No Opinione colleague. The compressor we tested at 2 stages, and the reason was that with only 1 stage we would have had too high pressure ratio across one single impeller, and that would make it let's say not particularly a nice impeller. So we distributed the delta P across two different stages. So that's the reason. You can do easily with 1, but then you get very low width at the end of the first stage. Rasmus, please.
I completely agree. Very often it's not a case of what a beautiful impeller would look like. It's more a compromise. You have to balance axial thrusts, so you at least have to have 2 stages or multiply 2. Then on the next one is we tend to start always taking one known impeller from our family of impellers. There is no special sCO2 impeller, so we see which one of the existing ones matches best, and then maybe fine-tune this to the eventual job. And the sad but true, the picture I have shown on this cross-sectional, that's not an sCO2 machine. That was a hydrocarbon machine. So don't take that picture as 100% reference for sCO2. Actually, very often it's also the case that the high torque requires thicker blades. So you cannot use the most filigrane blades for that. Or the high momentum then on the blades.
Thank you very much. I hope that I gave you, Gabriele, clear answers. So yes. Meanwhile, okay, very good. Meanwhile, I received a question for adding some references about the models. I put them. I put, let's say, the indication of a paper about the barotropic model.
I suppose that if there are no other questions that anyone wants to answer, we can conclude. So let me ask you, the speakers, do you have any parting message, anything that you still want to say before we formally say goodbye?
I can only say that there is still a lot of things to do with supercritical CO2. I mean, a lot of all the aspects are also still about the compressor and pumps. There is still a lot of things to do, and it is encouraging that we have seen a lot of recent successes, and this indicate that there is a lot of things to do, but it is worth doing.
But if nobody's making question, I'll do it another one. Actually, I have also some comment for Professor Persico. You mentioned about the cavitation. It's not clear from your explanation if the cavitation is a detrimental problem, let's say, for compressors. So it's something that you can live with, or it is making, let's say, is such to determine some catastrophic failure to the impeller. So like, for example, for pumps. And then one comment, I noticed that there is a little bit of mismatch between your, let's say, map in terms of power RPM and what has been done by Baker Hughes, let's say, in terms of RPM diameters. So it seems that you, for example, for 10 megawatt, you wouldn't run at 14,000 RPM. You would run at much higher speed. So if you can comment on that.
Yes, I can. Let me answer the first. So I mean, you're right that it is still not clear if we can accept cavitation or condensation or not. But for sure, we know that the most traumatic and catastrophic effect of cavitation, for example, in liquid pumps, is given by the fact that you have huge bubbles that move and implode. And this is mainly driven by the fact that you have a huge difference in specific volume between a vapor and liquid once cavitation occurs. As you approach the critical point, this difference reduces. So the bubbles remain smaller and dispersed in the main phase. So in this condition, of course, they can create a forcing, but but we expect that they will not damage the machine as it could occur in the case of a liquid pump. And for this reason, I mentioned that the perspective at which we should look at the cavitation in SO2 compressors and in CO2 pumps must be quite different. So in the case of pump, I think we really try to identify rules like the NPSH to avoid cavitation. In the case of compressors, at a certain degree, I think we can leave it. We can live with it and accept, but of course, a lot of experience is still needed with a long time of operation to assess this statement. We have experience with other fluids in similar conditions, but this is a very, as Rasmus was saying, supercritical CO2 is quite special fluid, and we still need to let's say, see in the future what will it be. But we hope that we can accept this, because this is very important, because if we should avoid at all any phase change and cavitation, this means that we stay with the intake state very far, relatively far from the saturation. And this reduces the thermodynamic advantage of the cycle because it increases the work exchange of the compressor. So this is a trade-off between the efficiency of the cycle, the reliability of the machine. You touched a very important topic, but I mean, I think we can be let's say positive about that in the future. For the second point, another time you're right, and we also noted about this mismatch when we were sharing our presentation, but we decided to keep. And thank you for raising this point, because the table I showed about the selection of the compressor, because I think you're referring to that, is from a very relevant book published in 2017. And based on expectations, on early experiences, now, I mean, they are not anymore expectation. Now there are research projects that are revising these ideas. So you see a picture of the effect of 5 years of development in that numbers. So the mismatch comes from the fact that the technology is very early and is growing very fast. So for sure, you should rely more on the most recent developments.
May I comment on this as well? Once the physics and the thermodynamic behind it in a theoretical way pointed to a potential danger in the way of operation, then you of course can address this by different ways of shaping the machine. Like Marco, I think you addressed this by using splitter blades. You can as well have it by a different inlet geometry of the machine, not accelerating the flow that high, so the pressure drop will not be that severe and so on. So again, you need to be aware you're on a very thin line you're walking, but if you not walk on that line, then you're losing per se efficiency.
Thank you.
We still have quite high number of participants, so I think that that's very flattering for us that you find our webinar interesting. So I think that we can still allow one question if someone wants to ask. Looks like it's not the case. So I think we can conclude, unless you still want to say something, Giacomo, Marco, Rasmus.
I think we started with some closing remarks from everybody, and then. So I started already. Then I will keep going. From our perspective, it's a true evolution. As I said, started decades ago, And every time we do something new, we get one more tool and one more aspect, what can go and what cannot go in our toolbox. So putting this all together will not bring the big leap, but always better machines, getting closer to real limitations. And once we found a real limitation, we have to come up with a new solution, and then we manage the next step. So this cooperation between academic research that points the technology providers in the right direction and then verify it in the real life, that's paving the road.
Just say that, as Rasmus pointed out, CO2 compression is something we do in the industry, and we have been doing it for a long time, but mainly was for process, not for power production. So we need to repurpose what we learned, find new way of using what we already researched in the past, learn how to ride the horse of everyday intake at the critical point, which is a wild horse. So a lot of things need to be adjusted using what we know and investing in what still has to be proven up to TRL7, because ideally, that's what we want to do, and we want to breach the barrier in between research and commercial. So we want to make it available for end use. So that's the goal.
So I can say to conclude, to conclude, I can only say that we did not discuss much about the modeling aspects from the fluid dynamic point of view and the structural point of view, but also this is a heavy research area. It has been a lot of object of a lot of research in the last years, because it was important to have the first model that were working properly. It was very important to see the first experiments of these machines tested and published with positive outlook. So I think a lot of work has been done in very small amount of time, and this is indicates that the tools are however in a good shape and can support the development of the technology, because this is important for a technology can be based on a scientifically sound methodology and reliable from the quantitative point of view.
Before we say goodbye, so thank you very much to all the three speakers for your for sharing your priceless experience and for preparation of this webinar with us, with ETN Global. We really appreciate it. But I would also like to thank to our audience. We are very flattered to have seen you so numerous. Thank you very much for your engagement and for your interest and curiosity. And we very much hope to see you next time, which brings me to the explanation of the next time will be, because as we said, this will be a quarterly webinar series, so we are hoping to meet you again in about 3 months. We are targeting end February, and we continue talking about the component challenges. So the next challenge and the next component will be heat exchangers and recuperators. So as we have your contact details, you will be contacted once the exact date will be known, and we will obviously keep contacting you for who the speakers will be, and we will remind you about the webinar. So thank you very much, and see you again. Have a nice afternoon.
Thank you, everybody. Goodbye.
Goodbye.
Goodbye, everybody.
Thank you. Bye-bye.
Bye, and thank you.
Thank
Goodbye.
you.
Thank you very much, Prof.
Thank you. Bye.